Done.
Okay.
Very good morning for fun.
So what we're going to discuss today is, we'll begin with the ITF, that is the inverse trigonometric functions, and we'll be discussing how do we go about defining their derivatives or calculating their derivatives, and then we'll look at a few more integrals. In the last class we practiced a few, but still we're going to take a look on a few more integrals, and then I'll give you a bit of an introduction of central force motion. How will we go about dealing with central force motion? What exactly do we mean when we say central force? So, I asked you these two questions: that what is the antiderivative of secant x and what is the antiderivative of cosecant x? These two are the answers that we got, and we will check whether we are right or wrong. But for that, like I said, a good way to going about calculating integrals is to calculate derivatives, because derivatives and antiderivatives or integrals are rather opposite of one another. So, I would like a little help from you people, because as I've said, on multiple events, my memory is weak. So what's the derivative of sin x? Okay, so we have cosine x. And what's the derivative of cosine x? Minus sin x. What is the derivative of tangent x?
Secant square x.
Secant square x. What is the derivative of cotangent x?
Minus cosec square x.
Minus cosecant square x. And what is the derivative of secant x?
Minus ln.
Secant x.
इसमें
And
secant.
I heard an ln there, and that is completely fine, but be clear, that is exactly why I am reiterating the derivatives, that be very clear about what's the derivative of what and what's the integral or antiderivative of what, because you might get confused there. But anyways, if you ever find this troubling, all you got to do is write it as 1 over cosecant square x. You'll write a cosecant square x. The derivative of 1 is 0, minus you will keep 1 as it is, and you will write the sine over cos would be tan, and the left cos can be written as a secant. So you have got tan x secant x. That is how quick you need to be. So in case of, we are all clear on that? Anybody got any problem with this? Yep. So how we did this is that this is 1 over cosine x, which is secant x, and the prime represents that we are calculating its derivative. So the chain rule tells us that d of, let us say, or rather I should directly write u over v prime is given by u prime v prime minus u times v prime whole over v squared. So our u is 1 here and our v is cosecant x. So first of all, the v squared is cosecant square x, and then the derivative of u, but u is 1, which is a constant, so the derivative is 0. So we ignore this term, we get the negative sign, we write u as it is, that is 1 here, this is 1 times the derivative of cosecant x, that is minus of sin x. So minus and minus, it becomes a positive sin x, and then I write this as sin x into upon cos x times 1 over cos x. So sin x upon cos x becomes tan x, and 1 over cos x becomes secant x. So we have got secant x tan x. So I need you to practice these as well. So try to remember it, but in case you forget these in the examination, you should be capable of deriving them on your own. So we have d over dx. What's left? Cosec x. And what's the derivative of cosec x?
Minus cos x cot x.
So again, in case you did not yesterday, note it down right now, because we will be needing these a lot. So first and foremost, we'll discuss what are inverse. No, it's fine. The point is that the derivative of cosecant x is minus cosec x cot x. So the integral of this would be, or rather you were confused here, that the integral of cosecant square x would be minus cot x plus c. But what I was asking was the integral of cosec x, not cosecant square x. as you know, we define functions so that I have two sets, a set A, a set B. Both of these have some elements, and here I have, let us say A, B, C, D, E, F, G, H, I, J, K, and L. So I define a function. Like I said, in order for a function to be defined, what I need is that all the elements in the first set, the set from which we are defining the function, because a function from set A to B and a function from B to A, these are two completely different things. So it is important which is our first set. It may even be the case that you may be able to define a function from A to B but not from B to A. So we want all these elements to be mapped, and we map them in some way. Another condition, except for all of these to be mapped, is that they should only be mapped to a single element here. Two of them can be mapped to the same element, but it should not be the case that the one here is mapped to two elements here. One input only produces one output. Two different inputs can produce the same output, but one input alone must produce only one output, a unique output. Now the thing is, we want to now define a function which reverses this function. We want an inverse per se. That is, when I say inverse, it kind of is the reverse. You can imagine that. So I want to define a function g, which I would like to be my inverse function. That is, think of it this way. That is, the switches here. The switches in this room, they correspond to a particular, what could you say, a particular appliance, a particular electrical appliance. I could say switch 1 corresponds to the AC, switch 2 corresponds to the fan, switch 3 corresponds to the projector, and switch 4 corresponds to the speakers per se. But then I may ask, another person may ask, what is the speaker connected to? As in, the speaker corresponds to which switch? So you'll say the speaker corresponds to switch 4. You may ask, what does which switch does the projector correspond to? You would say switch 3. So what we are trying to do is, we are trying to build a reverse function such that is f of d, that is, we have named the function f. So f of d, if it is I, then our inverse function g of I should give us back d. So we are trying to, in some sense, trying to build a reverse function. But then yet again, we'll have to look at what conditions this g must satisfy for the inverse to be even defined in the first place. So now if you look at it, like I said, all the inputs, because now this has become our input, because the function is defined in this way. The function is defined from B to A. So now this has become our input, and like I said, each input must produce only one output. But here in the original function, if D and E are both linked back to E, linked to E, then E will go back to D and E, and thus G won't be a function. So for that, we must also ensure that in our original function, one input is only exclusively linked to one output. What I'm trying to say is, if D is linked to I, E cannot be linked to E. So for G to be a function in the first place, what we see is that we need F to be an injective function such that when I took one of the inputs from here, it must go exclusively to a single element here, in the sense that I cannot have D and E, though F would still be defined, but for G to be defined, I cannot have D and E both going to E. If one of them goes to E, if D goes to E, E must go someplace else. So we define that as injectivity of F. What I mean is that if I find two elements producing the same output, I am wrong in the sense that it was the same element to begin with. What I'm trying to say is that if I take in one element, I get one output, then no other element must produce the same output. That is the condition. That is, we need the function to be injective. But yet again, for G to be a function, like I said, all the elements must be linked. And like I said, if all the elements are linked, what we are thinking is, if A goes to G, then for our new function, which is G, I have already used G, so let us call this capital G. So capital G of small g must give me back A. But for that to be defined, for this to be a function, I need all of these to be sensible inputs, that for all of these I must get an output. But then when I look back at the original function, I get another condition. That is, so that when I deal with this function, I can get an output for each and every function. What I would require for the original function is that it leaves out no output here. In the sense that there must always be some element here which links to each and every element here. So that is what we call surjectivity. Mathematically, what we write is that is for all. This is read as for all. Small b belonging to b. That is for any element belonging to this set. This is read as there exists. There exists some a belonging to a, which means for all element belonging to this set B, there must be at least one element A here such that f of A yields B. So if you look at it, if I combine these two conditions, this is called the condition of injectivity, this is called the condition of surjectivity. Together they are called the condition of bijectivity. That is, if a function satisfies them both, that a function is injective as well as surjective, we call the function to be bijective. And what do these two imply? So what it is implying is that if I was to draw two sets, let us say I have a B here and I draw A, B, C, D here. Surjectivity implies that all the elements here must be linked to some element here. But then injectivity implies at the same time that these linking, they cannot be to the same element, though it would also imply that this would no more be a function. But still, but then yet again we cannot have any more elements here, because then, like I said, for the function to be defined, all the elements must be linked. So what bijectivity implies is something that we call one-to-one correspondence. That is, in both of these sets, we have unique pairs. It's almost like this, that I take up this entire class and I begin pairing up people. So let us say I began to pair you with you to you. So I can go back as well, because you guys are now a unique pair. I will make sure that you are not linked to anybody else and you are not linked to anybody else. So what we are seeing is that we have a set of unique pairs. That is what it means to be bijective. I would like to illustrate this further by giving an example of a bijective function. The very convenient bijective function is the function y equals x, because any point on this line is unique. That is, the point 4, 4 lies on this line, but then I am certain that 4 does not lie with any point, as in for this x I am getting no other y, as well as for this y I am getting no other x. So for all the x's and y's I have unique pairing, as in any y is linked to some x, but then that x is not linked to any other y. So there's a one-to-one correspondence, as in all the elements of this set are linked to all the elements of this set, such that each pairing is unique in some sense. You cannot pinpoint any point on this line such that the x coordinates or the y coordinates would be same. So this is a bijective function. If this is a bijective function, I can reverse it the other way around as well. If I know the pairs are unique, that is, if the pairs are x and y and these are unique, I can switch the pairs to be y comma x. That is the beauty of this function in some senses, that the inverse of this function is also the function y equals x. Because if I turn this in some sense, if this becomes my x-axis and this becomes my y-axis, this line would still be y equals x. So basically I changed the domain and the codomain, and what I saw was, since there was a unique pairing, I still have a function. This is a special function, that is, the inverse of the function is the same as the function itself. But in some cases we might find that the inverse of the function is not the same as the original function. So now we understand what an inverse is. So we will like to talk about inverse trigonometric functions. So I would directly illustrate this with the example of the trigonometric function, which happens to be sin x. Now if I was to define an inverse of this function, that is, if sin pi by 2 equals 1 I want a function sine inverse 1 which gives me back my pi by 2. So in some sense I'm asking the question, for this value of sine, for what angle, that is pi by 2 here, for what angle will I get the value of sine to be 1? That is the question that I'm asking. But yet again, what we'll have to do is, we'll have to look for unique pairs. But these unique pairs do not exist if we consider the entire sine x, because if I was to further draw this graph, it is for two x's that we are getting the y1, that is pi by 2. This happens to be pi, this happens to be 2 pi, this is 5 pi by 2. So both pi by 2 and 5 pi by 2 yield me 1. So if I ask sine inverse 1, I can get pi by 2, I can get 5 pi by 2, and I can go on forever since sine is periodic with a period of 2 pi. So I can go on forever. So then sine inverse would not act as a function, because like I said, for a function to be defined, each input must only yield one unique output. So what we rather do is, we consider that can we somehow change the, the codomain itself, such that we'll be able to yield the right angles. For example, I know on pi by 2, I am getting, let's say, 1. On 5 by 2, I am getting 1. So what if I do not consider 5 pi by 2 to begin with? That is, I restrict the graph until this point. But then I want to consider as many values of sine as possible. In the sense, because if I consider only my graph until this point, I can leave out this point. But this only yields the positive values of the sine curve. I want values from -1 to 1. I want to create a function such that I can input any value in the interval, in the closed interval -1 to 1, and it would yield a unique angle such that the sine of that angle would give me my original input. Is everybody at least clear on that? So what I'm trying to do now is, for 0 to 1, I consider my codomain, because remember this is the domain here, but for the sine inverse function this will become the domain, and this then will become the codomain. So what I'm restricting is that I'm fixing something called a principal value, that whenever somebody asks me sine inverse of 1, I must answer only those angles which lie up till pi by 2. But then I also need angles for the negative value of sine curve. So then I take this part of the curve. So this happens to be minus pi by 2. So what I can see is that I have restricted my domain is still 1 to -1, but codomain has been restricted, as in I've got a principal codomain which is minus pi by 2. In more easier words, like I said, what does the sine inverse function ask us? When I say y equals sine inverse of x, all the function is asking me is that give me a y such that when I take the sine of y, I get back x. To reiterate, sine inverse of 1 would be pi by 2, since sine pi by 2 would be equal to 1. So in order to rewrite this function, I would write sine y equals x. But like I said, for sine particularly, we have restricted that the answer that I get, because like I said, we can get multiple answers. I can get pi by 2 plus 2 and pi as many answers as I want. So I fix the principal value logically, because I can see in order for the values from 0 to 1, I take 0 to pi by 2. I don't want to go any further because then the values would start repeating themselves. So I come back and I also get the values from 0 to -1. So yet again in mathematics we do the most natural thing possible. So when we try to restrict our codomain of the of the sine inverse function, we get that our codomain should be minus pi by 2 to pi by 2. So in some sense, when I ask you sine inverse of 1, you are going to tell me that it is pi by 2 and not the other values. So I have fixed it this way. Now in order to understand whether everybody in the class has got this or not, I would like to ask you a question again. This is the cosine curve. Y equals cosine of x. Now, using logic, this is 0, this is pi by 2, this is pi, this is 3 pi by 2, this is minus pi by 2. Now, yet again, using the same logic that I use, I would like you to tell me what should the principal codomain, what should be the codomain of cosine inverse x be, given the curve of the cosine graph. Yet again, remember that we need values, we need angles for all values from 1 to minus 1. And what we are trying to do is we are trying to restrict in the sense that no value is repeated. Is that clear to everyone? So what do you suggest we consider the principal domain for the cosine curve? Right side of the x-axis, exactly. For the positive values, I go here.
We can also take the left one also, right?
Yeah, we do take the left one, but generally by convention we try to move towards the right because that is more natural to us. But then as I move to the left direction, yet again these values are being repeated. So I move further towards the right and I restrict myself here. So then the principal domain, codomain per to say of the cosine inverse x function, what I get it to be is 0 to pi, and just a second, no, not 0 to pi, is it 0 to pi? Yeah, it is 0 to pi. But on 0, cos 0 is 1 and cos pi is minus 1, fine. So we get 0 to pi. In a similar fashion, you could get the principal codomain of any trigonometric inverse function. Like I said, you want all the values, so you begin by moving to the right. And like I said, if in the sine case, we could not move any further to the right because the values would start repeat, you go back to the left. That is, you consider values, the negative values, that is the values behind 0. And in this fashion, you can determine the principal codomain. Yet again, to know whether everybody has understood this or not, the graph of tan x, if I can draw it properly, I always have trouble drawing it. This is pi by 2, this is negative pi by 2. What should we take the principal codomain of tan inverse x? I want one of you to raise up your hands and answer that for me. Yes?
Between the dotted lines.
Okay, so what we are going to do is, since the values go up till positive infinity and negative infinity, we begin moving to the right. We begin moving to the right. And we can go back further ahead as well, we would still get new values. But what we'd rather choose is we want not a discontinuous, because at pi by 2 tangent is not defined. So we do not want it to be discontinuous, we want a continuous interval in some sense. So we go back rather, because in that sense we have the discontinuities here and we have an entire continuous function here. So it is minus pi by 2. But note that unlike sine and cosine, here we have open intervals. That is, tangent inverse of infinity per se does not exist, or I should rather say, tan of pi by 2 or minus pi by 2, it does not exist. That is, these are values of tangent which are not defined. So, I believe now it is clear how the inverse trigonometric functions work. So, we will try to solve for their derivatives now. Start by saying that y is equal to sine inverse x, and yet again what is this function asking me? This function is asking me that give me an angle y such that when I consider sine y I get back x. So what I can write is sine y equals x, and I am free to differentiate on both the sides, so I differentiate with respect to x. So dx gets me 1. And when I differentiate sine y with respect to x, since y is another function and I am assuming that y would come out to be a function of x, I would use the chain rule. So I would differentiate sine y first of all with respect to its own variable, which is y, and that is going to yield me cosine y. And then I am going to multiply the derivative of that variable which I used here with respect to the original variable with respect to which I derivated or differentiated. So I get dy dx to be 1 over cosine y. And I know dy dx, since my y was sine inverse x, so this is nothing but the derivative of sine inverse x. So So I can write this to be dtx of sine inverse x. But the derivative of sine x happens to be cosine x. The derivative of tangent x happens to be secant square x. So we cannot say that the derivative of sine inverse x is a function of y. We need to put it back so that we can call it a function of x. And what information do we have here? The information we have here is sine y is equals to x. So I'll give you an easy method out. I consider a right angle triangle. I consider this to be my y, my angle y. So if I consider my hypotenuse to be 1, because if you remember, we define trigonometric functions is that we consider a circle and we have a vector that is at different angles, theta 1, theta 2, theta 3, and then we construct such triangles and we talk about the x coordinate, the y coordinate and the radius. Note that the radius is always positive, but the x coordinate and the y coordinate can be positive or negative for any angle. So I take this to be 1 because this is the hypotenuse, this is my radius. I can fix this, I am free to take whatever value I want. But if I take this in this manner, for sine y to be equal to x, I need the length of the perpendicular to be equal to mod x. I took mod x because sine y of x, x could be a negative coordinate as well. I do not want that. So I took mod x because if I take x, I am saying that the length is a negative value, which does not make any sense. So then what would this be? This would be, by Pythagoras theorem, 1 minus mod x squared. But then yet again, mod x squared and x squared are the same thing because minus 2 squared is 4 and mod minus 2 squared is also 4 and mod 2 squared is also 4. So mod x squared is the same as x squared. So this length I am getting to be under root of 1 minus x squared. Is that clear to everyone? Now I need to consider my cosine y. So I will say this is 1 and this is under root 1 minus x squared. So I can directly write my cosine y to be under root 1 minus x squared over 1. But is it a positive sign or a negative sign? Remember, this is very important that you always consider this to just be the length, and like I said here, the x coordinate can also be negative. So whether to put a plus sign or a minus sign. Now that is exactly why I went through the trouble of teaching you the codomains of these functions, because when I considered sine of x, or rather sine inverse of x, I said that we are only considering this part, that is, in our minds we are only considering the angles from minus pi by 2 to pi, and in this range I can assure you that cos is always positive. That is, in the range here, if I was to draw the graph, I would get something like this. This is the sine graph and this is the cosine graph. So what I can see is, in this range, cosine always happens to be positive. So thus, I can be free and I can just use the positive sign here. And this is my cosine of y. I put it here. And you get the sine inverse of x. That is, rather the derivative of sine inverse of x happens to be 1 over under root 1 minus x squared. So now it is your duty to verify all the derivatives. I'll simply give you the formulas, and in the formula you'll see modulus at a few places. And like I said, the modulus comes when you are not sure whether the value of the x coordinate or the y coordinate happens to be positive or negative. The modulus in the formula is just a consequence that we are not sure of what x might be. So if my memory serves me right, and I can get back my duster, I'll try to correctly write the formula, but I would like your help to ensure that I have written down the correct formulas. Sine inverse of x happens to be, like we saw right now, 1 over 1 minus x squared. Cosine inverse of x happens to be the negative of this. Tangent inverse x happens to be 1 over 1 plus x squared. Well, actually, these are derivatives, I'm sorry. These are not values. These the derivative, this bracket and prime, it just indicates the derivative of the set function. And then if I'm not wrong, the cotangent x derivative of that happens to be the negative of this. Is this correct? Are you all sure? And then we have, yet again, if my memory serves me right, I have secant inverse of x, the derivative of that happens to be 1 over mod x square root x square minus 1, and then I have cosecant inverse x, which is equals to the same thing, just that yet again with the negative sign. So if you can see here, the what could you say, the derivative of the cosine inverse is just the negative of the sine inverse, the same with the cotangent and tangent, and the same with the cosecant and secant. Even if you look at the name, it makes a lot of sense. Sine, cosine, tangent, cotangent, secant, cosecant. So the cos have all negative signs, so you might just work with the normal ones. If you remember these three ratios, the cos are just the negative, but remember for the inverse functions. So now we are done with the derivatives, and now using all of this, we would like to move on to the few integrals that we must still consider in order to be ready for our mid-semester examinations. What's the name of the course again? I thought I would stop writing it, but I'll still have to write it. That is the mathematical prerequisites for classical mechanics. Even I sometimes forget that. I don't know why I named it that way. It just sounded good. Sounded more like an official course. So, anyways, let us see. Now we'd like to deal with a few integrals. And like I said, we'll begin with the special secant x dx. And somebody needs to tell this to me very fast, especially at the math students. I'm looking at you. And I click the picture of the textbook. And I want to solve things from in there. And I made the mistake of not clicking the picture of the solution. So if I'm stuck, I'm stuck. So, guys, anybody? Yes, sir. Yeah, you have got the answer. Yeah, what's the answer? ln sin x.
Minus ln cos x.
So you're saying ln sin x, right? Or are you saying something else? You said natural log of sin x. Oh. We have natural log of sin x. Just sin x or mod sin x? Mod sin x. Now, because I don't want to let you down, I'll change the question itself. It is of cotangent x. But yeah, nice try there. Yeah, and who else said? You said something?
वो गलत था.
Sure, okay. But like I said, whenever you are confused कि वो गलत था या वो सही था, the most important theorem yet again, the fundamental theorem of calculus. If you are not certain about an integral, differentiate it and see whether you can reach back to the original function or not. If you differentiate the natural log of sin x, mod sin x, you are going to always reach back to cotangent x. So yet the end. So I get no answers and it's completely fine. And I've got secant x dx, and because I want to show you in maths we do the most natural thing, and I have a weak memory. So tell me, because I am supposed to differentiate a function and get secant x, right? So tell me, in the list that you have, which functions when differentiated yield a term of secant x. It is not required that it yields exactly secant x. Any term which involves secant x.
Secant x. Tan
So
x.
we have d dx tan x, which if I'm not wrong, please correct me if I am, is secant squared x, and d dx of secant x, which if I'm not wrong, correct me if I'm wrong. Am I right with both of these derivatives? Now I notice something, that is, both of them have a secant x term here. So what I'm going to do is, I'm trying to convert the secant x to secant squared x and secant x tan x, which is going to be pretty easy because the magic trick is I'm going to multiply it by 1. So multiplying by 1 changes nothing. So we all agree on this. And what I'm going to do is, I did nothing wrong. I just wrote 1 as y over y. It makes sense. These go divide and I get 0. It's fine up till this point. And then for the next trick, I'm going to multiply it in to yield both of these. I did nothing wrong till here. It's fine. And I know that I can break apart the sum, right? Because what I'm trying to say is that the integral of u plus v is the same as the integral of u and the integral of v. There should be a dx here or something like that, like dx and dx and dx. So yeah, so we are getting somewhere. And now for my next trick, to make things even easier, I'm going to assume something because, like I said, what did I say to you? This is why even things that seem very petty are important. I said that when we are trying to make a substitution, what we do is we try to look that something in the function when differentiated yields something else in the function. And I know that secant x yields this, and tangent x yields this. So I take this as my u and I differentiate, and we'll see if it works or not. The differentiation of secant x, ladies and gentlemen, happens to be secant x tangent x, and the differentiation of tan x happens to be secant squared x. But when I look carefully enough, this happens to be my numerator. So this becomes simply du when I consider this to be u and this is u. So I present before you from secant x dx, the integral, we have got to a very simple integral, that is 1 over u du. And I would like one of you to answer this. What is this going to be?
No u. And then u.
But I told you tomorrow that there needs to be a mod here. Because for u, for ln, the argument always is positive. But for 1 over u, you can also have minus 1 as u. So you have ln mod u. And then, because we did not put any limits here, we also have the constant of integration. So for that we have the constant of integration, but u is something that we assumed. U was never there to begin with. So the final answer, ladies and gentlemen, happens to be the integral of secant x dx is nothing but the natural log of secant x plus tangent x plus c, rather the modulus of this thing. So that is how you integrate secant x, and similarly you are also going to differentiate cosecant x, because if I am not wrong, what is the derivative of cosecant x? Minus cot x and cosec x, right? So similar to how here we had the derivative of sec x to be sec x plus sec x tan x. In the cosec x case, you'll have cosec x cot x, and similarly how here we have the derivative of tan x to be secant square x. You'll have the derivative of what to be cosecant square x again?
And cosec x minus cot x.
Sorry.
So cot.
What, the negative of cosecant square x. My memory is weak. What do I need to differentiate to get the negative of cosecant square x? Cot x. So for the cosecant x technique, or the trick, the magic trick, you are going to have to multiply it with cot x plus cos x. You are going to yet again assume this to be u, and you are going to get to the formula, which, if I am not wrong, can anybody remind me, or do I need to redo this entire calculation? I believe it is the negative of the ln entire thing, or rather the
cosec x plus cot x.
will be cosec x plus cot x here.
Minus cot x.
Minus. Oh. And do we have a negative sign here?
No.
So I am saved by my friends by my weak memory. They have saved me. That is the integrals of the secant x dx and the cosecant x dx. So I've given you these now. Now we'll move on to the questions. Yesterday I avoided the questions of cosecant x and secant x. This, if you're brave enough in the exam, you might try to redo this entire thing, which is a risk I would be willing to take because my memory does not serve me well. But it is for you to decide whether you want to take the same risk or not. But yeah, that is how we are going to do. But in the meantime, in order to save the time, please remember these two integrals so that we can summon them at will whenever required. And this becomes important to remember because sometimes in textbooks, you find very simple integrals. You find integrals like cosecant pi x minus 1 dx integral. And since I forgot to click the image of the solutions, you will have to help me here. Yet again, like I said, there are a few integrals that we are very well familiar with. So I can think of an integral of cosec L dl. So it might be sensible to take this entire thing as some other variable, some variable u or L, and then we can proceed. But even if we did proceed, let us say I consider u equals pi x minus 1, then I would get du to be pi times dx. This is what I'm going to get. So this integral then becomes cosec this is u, dx is du by pi, pi being a constant walks out, I'm left with du. But even when I have made this a known integral, I need to know the integral itself to be able to solve it. So either you can remember these formulas, or you could just go on with multiplying and dividing with cosecant x plus cotangent x, whichever you find more convenient. So that is that, and let us look at a few more interesting questions now. So the next question we are going to look at is rather a very interesting question, and I would like the maths folks to give it a try especially. And I hope that you don't get integrals in the exam like this, but if you do, I want you to be able to solve it, because I cannot make any promises. It's not me setting your paper. So we have cosecant x, sine of 3x and dx, and since this takes particularly long, I would give you 2 minutes for it. And it may not need 2 minutes, it's just that I'll give you a hint. This requires a trigonometric identity, and I always seem to forget that what that trigonometric identity is. So you'll have to use that here. So it takes me a little time to write out that trigonometric identity. I'll give you 2 minutes for that. Hey, no cheating. Just kidding, you made it. So, any answers?
मैं तो सही गई अब तो कोपन हो जाएगा
Just speak up, don't worry. If your answer is incorrect, I'll try to change the integral so that we get to the correct answers. Because I am different. If my students are wrong, they're not wrong, it's a typo. So, yeah. Go ahead. What's the answer?
ln cosecant x minus tan x
ln cosecant x
minus tan x
minus tan x
minus cos x by 3.
minus cos x by 3. I would like to correct myself. This is a mistake. There's no typo here. Because I'll have to conjure up an integral. And I may be able to.
ln वाला बंद हो गया.
Sorry?
tan x के बाद ही small बंद हो गया.
Okay, so fine. Then we'll differentiate.
10x के बाद.
So fine. Now, like I said, we can conjure up any answer so that the students, they do not make a mistake, but rather we'll call them a typo. So what can I do with this function here to get the correct integral? Because what I know is, what you are claiming is if I differentiate this, I'm supposed to get the thing here. So now guys, sorry? Cosec x plus tan x. If we say cosec x plus sin x, are we certain that we are going to get this thing? But fine, if I really want to get this thing, like I said, you guys are yet again forgetting the most fundamental theorem, and I believe you are trying to say that, right? We could do that, and that is one way to do it definitely. But what I'm trying to ask you right now is that I want to erase this and I want to ensure that Supriya's answer is correct. So what do I replace this with? Guys, this is very natural, come on.
It's plus sign.
No, it is the fundamental theorem of calculus itself. Like I said, what I'm looking for is that when I differentiate this, I'm going to get this. So let us differentiate this function, one of you, and we'll put it in here so that we know for a fact that Supriya's answer is correct. So if we differentiate this, whatever we get, we'll input this here, and then we'll be able to get what the integral should have been for Supriya's answer to be correct. But given right now, I claim that this is a typo, this was not the original question. But still, if this was the original question, let us consider that. So I would like to consider what the sine of 3x is.
3 sin x minus
3 sin x
4
minus
sin
sin
qx.
This is an identity, and in case you forget this identity, like I do every time, that is exactly why I gave you 2 minutes for it. You simply write this as sine x plus 2x, then you use sine a plus b, which is sine a cos b plus cos a sine b. You are going to get sine 2 theta and cos 2 theta. Yet again you use the same identity twice, and you change the sine 2 theta to 2 sine theta cos theta, and you change the cos 2 theta first to 2 cos square, no, you change the cos 2 theta to 1 minus 2 sine squared theta. And in case you are confused, I'll do that for you right here. So what I claim is, yet again, if this formula is correct, what I'm going to do now is, I'm going to put a and b both equal to x. So I get sine x plus x, which is sine 2x, and I'm going to get sine x, cos x, sine x, which is the same as 2 sine x, cosine x. So sine 2x is the same as 2 sine x, cosine x. Yes, sir?
Can we do with the by parts?
You could do this by parts, but right now, since a lot of integrals you won't need to do with by parts, that is why maybe I'll try to get into by parts.
By parts is going to make it a little bit complicated.
Of course it is, but like I said, the question was whether he can do it or not, and to answer, I don't know until I try. So we'll have to see, but I'm pretty sure, given my previous knowledge, I say until we try because most of you, I believe, would not have tried, would not even have studied integral by parts. That is why I'm trying to think from your perspective. But using my previous knowledge, but my memory is weak, so my previous knowledge is not as reliable as yours. I believe it can be done by integration by parts as well. But I would agree with our friend that it may make it a bit more complicated, but I'm not sure yet again. My memory is weak, I cannot know until I try. So here we have this. And the same way when you use the identity that cos of A plus B equals cos A cos B minus sin A sin B, and both of these have their own derivation, and let's not go into that. If you want, I would derive it for you. But if we take these formulas to be true, I can write cos 2x to be 1 minus 2 sin squared x, and sin 2x, like I said, becomes 2 sin x cos x, so I increase the power. So I have cosine squared x here, and I write that as 1 minus sin squared x. So here I get sin x minus 2 sin squared x, and I get sin x minus sin cubed x, and I believe on solving this one way or the other, but we had a 2 here as well. So we had a 2 here, and I believe on solving this you will be able to get back to this original identity. Are we clear on that? Any confusions? Fine. So now that we have this identity, it becomes easier, and I'll tell you why. And the reason why I choose to do it this way is to illustrate another point, that is something which you would have encountered while studying alternating currents and oscillations. We have to deal with integrals of the form, the integral of sin squared x dx, the integral of cosine squared dx, cosine square x dx. So what I'm trying to also do is, I get 3 sin x plus 4 sin cube x plus c, but then I need to multiply it with cosecant x, but cosecant x is nothing but sin x. So all I got to do is divide this entire thing. Do we have a c here? Why do I have a c here? That's from a previous question. So when I divide, what I get is 3 minus 4 sin square x dx, and in order to get to that, we'll have to integrate sin square x dx. So the reason I chose to go through this question in this way is I also want to illustrate to you that how are we supposed to solve the integrals of sin square x dx and cosine square dx. Back in our first semester, we were not taught oscillators, but if you are taught oscillators, and even if you are spared this semester, you will have a mandatory course next semester which is called electrodynamics. That course would not spare you, and you would have to solve integrals such as sin square x dx and cosine square dx. So this is going to help you. So I believe my friends to have told me the correct identity because I did not solve it until the last step. So cosecant x becomes 1 over sin x, and then sin 3x becomes 3 sin x plus 4 sin cube x, and we have an entire dx out here. The sin x's cancel, so I get 3 plus 4 sin square x dx. So I'm multiplying some sense the dx loosely speaking, so I get a 3 dx plus 4 being a constant self out, I get a sin squared x dx. Does everybody get till here? What I did was I used sin 3x to be equal to 3 sin x minus 4 sin cube x, which I told you how you're going to get to that, and then I divided by sin x because cosecant x is 1 over x. So I get 3 minus 4 sin squared x dx. I basically break the integral, like I said, integral of u plus v dx is the same as integral of u dx plus integral of v dx. So that is what I did here, and 3 and 4 being the constants walk out of the integral sign. So until here we are all clear and we do all agree, right? So when I integrate 3 dx, you all know I'm simply going to get 3x, and I'm going to get a constant plus c1, and when I'm going to integrate this, I'm going to get a constant plus c2, and collectively two constants adding up is also going to produce a constant. So I can directly integrate both of these and claim that whatever constant was produced, I clubbed them together to produce the constant c. Are we clear on that? So what we need at the moment, but since we are yet to integrate this, I'll call this c1 for the time being. What we need is sin squared x dx. But right now I told you something, which was 1 minus 2 sin squared x is the same as cos 2 theta. So cos a plus b is cos a cos b minus sin a sin b. Do we all agree? I keep a and b both to be equal to theta. So I get cos theta plus theta, which is cos 2 theta, equals to cos theta times cos theta minus sin theta times sin theta, which yields cos squared theta minus sin squared theta. I replace because I want answer in terms of sin squared, so I replace the cos squared theta with 1 minus sin squared theta. So I get 1 minus sin squared theta minus sin squared theta, which finally yields 1 minus 2 sin squared theta, which I wrote directly. Then from here I get sin squared x to be equal to 1 minus cosine of 2 theta, and if I'm not wrong, by 2. So we all agree here. And yet again I can break this down. I can write this as half and this times half as well. And I'm going to put it in here. I don't want to go through the trouble of solving all this, because yet again half times dx is going to yield half x, and then half times cos 2 theta dx. Like I said, you can substitute, you can keep 2 theta equals to u, and then you would get the same value. It's a basic substitution, and you will be able to solve it. Is that fine with everyone? So what I'm trying to say is, as the integrals get complicated, you will have to employ your information, or I should say knowledge, from other branches as well. You have to employ techniques from arithmetics, as in some manipulations or some toolkits from arithmetic, some arithmetic manipulations, some trigonometric identities, some exponential stuff, for example, the properties of natural law. For example, generally if I was to ask you the derivative of d a over x, you would say that this happens to be ln a times a raised to the x power. But I was to ask you to derive it, one of the ways to do it is this. I say that I can write a to the x to be equal to a raised to ln a to the x. Because like I said, what does ln a to the x mean? The real number which, when I raise e to the power of, is going to give me a to the power x, as in ln a equal b implies that when e is raised to the power of b, I get a. The same logic I am going to apply here. What this entire real number means is, when I raise this real number to the eth power, which is actually happening here, I would get back a to the x. So I am doing nothing wrong here. Then I'll use another property. The property is that if a is a constant, or I should rather use the word positive constant, x can leap up and it can come in front. That is, ln a raised to the x can be written as x times ln a, or rather mod a, because natural log only takes in positive numbers, and I could still have written, for example, ln 4 is something which is defined, but I can write ln 4 as ln minus 2 raised to the second power, and then if I do not include the mod a here, I can write this to be 2 times ln of minus 2, but ln of minus 2 is not defined because ln is only defined for numbers greater than 0. So thus, when I do this, I'll have to introduce a mod here. But generally, when we talk of a to the power x, we assume that a is positive to begin with, because if I consider, let us say, minus 2 raised to the x, it will not be defined on numbers such as x equals half, because that would mean square root of minus 2. I cannot write minus 2 raised to the 1/4, because that would mean the fourth root of a negative number, which is not a real number, and rather from this real line we'll move to an entire plane which is called the complex plane, but that you need not worry about right now. So what I'm trying to do is, whenever we talk about a to the x, because generally we talk about differentiation for continuous function, because if you remember, I even discussed this, that every continuous function need not be differentiable, but every differentiable function needs to be continuous. So if we are talking about the differentiation of a function, it is assumed, or we keep that in mind, that in whatever domain of it we are differentiating it, at least in that domain it needs to be continuous. And a to the x, if a is a positive number, is constant in is continuous in its entire domain. That is why we consider this to be positive. So we can directly write this as this. So I get e raised to x ln a, and now when I differentiate this, so what I've established is a raised to the x is equals to a raised to x times ln a. When I differentiate this, using chain rule, I write ex ln a. But then I need to differentiate x ln a. Ln a is a constant, and the differentiation of x is going to be, x is going to be 1. So I'll be left with a multiple of ln a. And now what is going to happen is, I just said that e raised to x ln a is the same as a raised to x. I'll put it back here, and I get ax. The differentiation of a raised to the x is a raised to the x times ln a, like we claimed initially. But in order to get to that, we had to use the assumption that this identity is true. That is, ln a to a raised to the x is the same as x times ln a. Are we clear on that? So what I'm trying to do is, calculus is not difficult on its own. Rather, it is a very easy and intuitive subject. People think calculus is non-intuitive, but I believe it is one of the most intuitive things out there. But it becomes difficult, not because calculus is difficult. It becomes difficult when we do not know how do we complete a square, how do we use the rationality of numbers, how do we use something else. As in this case, how do we know that sine 3x is the same as 3 sine x minus 4 sine cubed x? How do we know which are the right substitutions to make in a question? That is how calculus becomes difficult. Calculus is not difficult on its own. It is deemed as difficult because it requires your knowledge from all specific subjects. It might be that you may come up to me with an integral and I may not very well be able to solve it, or even your professors may not be very well able to solve it. Not that because we do not understand calculus, but rather the knowledge, the arithmetic manipulation comes from some other branch that either people like me have not read or your professors may have forgotten. But if your Professor Sheath, well, that is a different story. Then we'll consider a few more questions for today, and we'll talk a little about the central force motion, and then we'll go back to our rooms and rest. At least I would. So then, I want one of you to solve this for me. It is the integral of x over x plus 1 dx. And this is an easy one, so I'll give you 40 seconds for it.
X minus ln or mod of x plus 1 plus c.
Sorry, x minus
ln mod of x plus 1.
ln
Mod of x plus 1 plus c.
plus c.
Yeah.
So this is one of the candidates, and we'll see whether we can get to that or not. So what I can see here is the manipulation from the arithmetics that we have seen. That is, I see an x above here alone, and I see a x plus 1 below here. Even if I was to substitute x plus 1 to be my u, when I differentiate it, I would get du equals dx, but I want an x dx. So in my mind, what I'm thinking is, I need the numerator to not be x, because I want my denominator, in some sense, I can conjure up an approach, and this may be wrong, because it may be in a lot of cases. What I'm conjuring up in my mind is, I want my numerator to be left alone. And how I'm going to do it is very simple. Plus 1 minus 1 equals 0. I merely added 0 in the numerator, thereby not changing the numerator at all. But then I'm going to separate the fraction. And it is going to be x plus 1 upon x plus 1 minus 1 x plus 1 dx. This. So I know this is going to become 1, which is easy to integrate. It's going to be x. And I know this right here, since I can take x plus 1 to be u, and when I differentiate, I would directly get du equals dx. So I know I will be able to solve this very well as well. A question may be, when you divide x plus 1 from the numerator and the denominator, you assume x plus 1 is not equals to 0. And you may ask, what about the case where x plus 1 is not equal to 0? And I claim that the question given to me is wrong, because I was given the question x over x plus 1 dx. So if x plus 1 is 0, the question is not defined to begin with. And here I get 1 dx minus 1 over x plus 1 dx. Like initially planned, 1 dx yields x, and I have a minus here. Yeah, I have a minus here. And I take x plus 1 to be my u. So u is x plus 1, du is directly dx, and then that integral becomes 1 over u du, which I know happens to be ln of mod u, and u was x plus 1, so I get ln plus mod x plus 1, ln of mod x plus 1, and this is a minus sign here, and this becomes ln of mod x plus 1 plus c. So yes, the proposed answer by your batchmate was correct. What's your name again, ma'am?
Anitya.
Anitya.
Nitya.
Nitya. So I'm pronouncing that right? So Nitya, congrats, you were able to solve this. So very well, I believe all of you are very well prepped for the mid-semester examination. Let us try to do a few more questions in the time that we have. I plan to mess with you till 7:10, so we'll solve 1 or 2 more integrals, and then we'll take a look at central force motion. Remember, this has limit, this is a definite integral, so your answer won't be a function, there would be no concept of integration involved, it needs to just be a real number. Let us see how you go about solving this. Just a little reminder, as for the integration by parts, I'll not take the risk of not teaching you before the mid-semester. That was what I was thinking. So I'll talk to Professor Sheen and I'll ask him if you guys are expected to be able to solve integration by parts on the paper. If he says yes, I'll teach that to you tomorrow. If not, we'll move forward with central force motion. For integration, I have taught you most of what you need to. You need to be able to make the right substitutions. You need to be able to remember formulas from trigonometry. You need to be able to remember a little bit of manipulation, separating out the fractions and adding and subtracting numbers, multiplying and dividing by something, remembering the standard formulas and using the fundamental theorem of calculus so that you could conjure up a function which, when differentiated, gives you back this thing which has the fancy name of the integrand. Any answers? Okay, so any answers up till this point, or do I begin solving this? Anybody? Okay. So yet again, what comes to my mind first is, like I said, I want to make some sort of substitution so that when differentiating something, I get something. And generally what happens is when I differentiate u, I get du equals something of x. And generally what happens is, like let us say if we have a square here and we have a x in the numerator, we take the denominator to be equal to our u, when we differentiate it, x square is transformed into x, and thus we can use x dx something. But here we rather see something else, that is we have a x here and x squared here. But this is similar to something which we saw last time as well. That is we had x in the numerator and x in the denominator as well. For those of you who are tempted to take x directly equals to u and deal with x squared, all you are going to end up with is going to be just a change of variable, because if I just put in x equals to u, I am not helping the question. This just becomes u, this just becomes u, this just becomes du. So it is the same question, no progress is made. So yet again, like I said, the arithmetic manipulations, and this is the beauty of maths. Now we need to go back to your childhood, and I need you to perform something which is called the long division of polynomials. That is, I'm trying to divide this entire thing, this thing by this thing, so that I can get some sort of x in the numerator and see if that helps me. So I need a little assistance here. What should go in my quotient?
2x.
Okay. So 2x times 2x is?
4x.
Makes sense. And 3 times 2x is?
6x.
Okay, it makes sense. And that's a minus here, minus here. This cancels out. I'm left with minus 6x, minus 7. And then what goes here?
Minus 3.
Minus 3. So minus 3 times 2x is minus 6x. And 3 times minus 3 is? I consider the pluses here. This cancel out and I'm left with plus 12. So now I know that this thing is this, yeah. It is, if I divide by this, that is what's here, or rather the way I'm going to write it is to make it more explicit. So I leave the denominator as it is, and I write the numerator as the quotient times the quotient times the, what do you call this again? I do not remember. Divisor. 2x plus 3 plus the remainder, which is 2 dx. Yet again a separation is performed. You have minus 1 here, you have 3 here. The 2x plus 3 is cancelled out. You are left with 2x minus 3 and plus here you are left out with 2x plus 3 dx. And I believe it does not seem so hard right now, because the dx in some sense, loosely speaking, comes inside. You have 2x dx can be done, minus 3 dx can be done, 2 over 2x plus 3 dx. I take this to be my u. When I differentiate, I directly get 2 dx, I get my du, and I solve and I get my answer. So it wasn't that it was calculus that you did not understand, it was that you forgot that this exists. So like I said, calculus is not tough on its own. It's just the biryani of mathematics. That is, you need something from all the branches and you mix it and you get this beautiful flavor, which if cooked properly, you find it great. But if not cooked properly, it hurts a little and gets you negative points. So with that, I'll let you be with the integrals. The textbook that I personally prefer, I'll send you the integrals. You might try them out. You're free to try them out. But the point is, I believe you know enough integration by this point. That is what you need to work on rather is when you solve an integration question. This is why I told you that when you are stuck in this question, for example, the question here which I raised, you got stuck in this question. But what was it that you were not able to think? Because you may say that I'm bad at integration, but the truth of the fact is you're not bad at integration. You forgot this. That is why mathematics, whenever you deal with a question and you're not able to solve it and you take a look at its solution, what you think of is what you want in your brain is which part could I not conjure up in my mind? What was the part that my thought process of solving the question missed? And then, now that you have solved this question once, so the next time if you are not able to solve something by substitution, if you cannot think of something, In your mind, you may find another approach that what if the denominator, the numerator, it has greater power, and on taking the denominator as u, I'm not able to get it. What if I try to long divide this entire thing and I get something like this, which is way more convenient to integrate? So that is how you go about it. Same with trigonometry. You see sine 3x, a bit difficult to integrate. Let us break it down to the normal functions. You see sine square x, a bit difficult to differentiate. You break it down into 1 and cos 2 theta upon 2, whatever that was. The same goes for cos squared x. So that is how you are to deal with integrals. And like I said, integral is a very mechanical work, something like almost learning how to bat or to throw a punch. I can give you all the theory you want, but the more you practice, the better you are going to get. If you see, let us say UFC, all day long, you still won't learn mixed martial arts. You'll have to get into the ring and you'll have to throw a few punches yourself. The more punches you throw, the more strength, the more endurance you gain. So that is what is to be done with the integrals as well. And now to the most interesting part, the part that I gave up on in my first mid-sem and went to sleep, something which goes by the name of central force motion. And the beauty of the first paper was that central force motion was never used. The only place central force motion was used was that is the only thing from central force motion in the entire paper. But I do not think you guys would be as lucky as me. So please don't go back to your rooms and sleep before studying central force motion for your exams. So right now I have 38 minutes. I would like to build some intuition of the central force motion. And then in the next upcoming classes, we'll deal with all sorts of things which the central force motion is involved with. So here's the thing. When you were taught gravitational electrostatic forces, that is the Coulombic electromagnetic force, in our 11th and 12th, if you studied through textbooks, maybe even in your institutes, maybe if you watched a YouTube one-shot, there used to be this big heading here, properties of the Coulombic force, and you were told to write a few points. So there was this one point which was very peculiar, that it acts in the direction along the line connecting the 2 points. That is, what was claimed was this is a point particle, this is a point particle, and what was claimed that the Coulombic and the electrostatic force acted along the line joining the center. And ladies and gentlemen, that is central force motion. As in, though it may seem difficult, but central force motion is something that you have been dealing with since you were in 11th grade. If thought about in the right manner, central force motion should rather be the easiest topic because it is something that you are already very well familiar with. But then, in this love story, we have rather a triangle. So here are you, and here is central force motion, and here is plane polar coordinates. That is, you know everything that you need to know about central force motion, but because central force motion is nothing but gravitation and electrostatic forces. But then this, I have not used any words here, but this disturbs us a lot. We do not get how does the theta dot come about? Why do we have r square? Why does the r theta dot square appear? It does not make any sense, and it would make sense if you start thinking in terms of plane polar coordinates, if you start thinking in terms of the definition. That is, this is exactly why, if you remember the plane polar coordinates class, I said that if you have understood nothing until now, it is completely fine. But there's a box that you need to remember. I'm missing a term here. This box was very important. This is all you need, because when you talk about the kinetic energy, the kinetic energy is very simple. What's the formula for kinetic energy? v squared, and if I consider the v vector, any vector, when I take the dot product with itself, I get a times cos 0, because both the vectors are in the same direction since they are the same vector. So I get square of the magnitude. So if I want v squared, I want the square of the magnitude of this vector. And since both of these are perpendicular vectors, the magnitude of v is going to be r dot squared, the under root, forgive me, r dot squared plus r theta dot squared. So this is the magnitude of v, because like I said, these two are perpendicular vectors, perpendicular unit vectors, and if I was to give you 3x cap plus 4y cap and ask you the magnitude, you would say under root 3 squared plus 4 squared. Well, this is my 3, this is my 4, and the x cap and y cap have been replaced by two other pair of mutual perpendicular unit vectors. But then, like I said, I need a v squared there, so I square the magnitude, and I get r dot squared plus r theta dot squared. So simply, I can write the kinetic energy to be, and this, when directly written in the notes, might have troubled you. Then I was to ask you about something called the gravitational potential energy. That is, if I have a point mass m here at a distance r, what is the gravitational potential energy? Well, of course, for potential energy, I need some other term as well. We could consider the potential as well, but let me say gravitational potential. What is the gravitational potential at this point? So you know minus Cm by r, but how do we get to that? So I write something along these lines. And then I integrate to get here. And what we used to do was, if I was to write dr in those terms, how do I write dr in that term? Well, let us say I consider it to be dr r cap. The r caps disappear because the magnitude is 1. 1 times cos 0 is 1. And I'm left with this. And when you integrated this, you got your answer. It may have been a minus here, I'm not sure, but the point I'm trying to iterate is, it is nothing different. All that happens here is, this is replaced by a function of r. That is all it is. So whether we talk about the potential energy, the kinetic energy, the potential energy plots, the plane polar coordinates, the angular momentum. For example, if I was to talk about this, here's the sun, which I assume to be fixed. Here's the earth performing circular motion around it. This is the difference, the distance r between the sun and the earth. What is the angular momentum here? mvr. But at the same time, you would claim r to be v to be r omega, right? Omega is nothing but what you call theta dot squared. So you get a very familiar expression. The point I'm trying to make here is that it is all way too familiar. Maybe the reason why we do not understand central force motion is because it is so familiar. For example, if I was to ask you, what's 21 divided by 7? But the way we used to do it, if we were to go behind the work, yes sir? M r square omega. Oh, really sorry. Thank you for the correction. So the point I'm trying to make is, if I was to do it as a middle schooler per se, I was to fine, let's divide it by 2, and it's not divisible by 2, so I'll give it a 0 and I'll consider this entire thing. And 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21. So I get a 3 here, I divide it and I write 21 to be 7 times 3, and then you could consider that 21 over 7 is 3. That is the entire point. Exactly, that is exactly what I wanted to hear. Central force motion is overcomplicated, a very simple thing. In fact, in your studies of central force motion, you don't even consider the other forces. For example, I believe in the class you would only consider the forces of this form, K over R squared. Now why is that? Because this is the way Coulombic forces are, this is the way gravitational forces are. You didn't even go far enough to consider this. K over R to the raised to be 7, which you will consider in a few cases, especially when you study nuclear physics. But that is not the scope right now. The point I'm trying to make is, simply you were lied, your what do you say, the Coulombic constant, that is 1 by 4 pi epsilon naught times Q1 Q2 was simply written as R. Your minus G M1 M2 was simply written as K, sorry, not as R, rather as K, and minus G M1 M2 was written as K, and you got confused. What has happened is we are just overcomplicating simple things. We are trying to talk about general things. So in order to understand central force motion, what you rather need to do is not to learn more advanced stuff, but rather to recall more elementary stuff. That is what you did in your gravitational chapter, what you did in the chapter of your electrostatic interactions, and you will be able to very well tackle central force motion. So that is why I wanted to take this moment, because especially the people who attend my classes, before we move on to the next class, I also want you to be confident that yes, this is something that you can tackle. It's not as complicated as it looks. Thank you all.